in our discussion, let us learn something about the first order reaction. Let us go for first order reaction. So, in this first order reaction, suppose for example, if I am taking reactant A, we take A gives rise to products. If reactant A is giving rise to product, in the initial stage, initial stages, let the reactant has a concentration equal to A moles per liter, A moles per liter at a time, that means that when the time is 0 seconds, here no amount of product has been formed. So, 0 we will mark it as 0 moles per liter when the time is 0 seconds. Now, after a time lapse, say after a time lapse of any amount of time lapse you can take, say I am taking 10 seconds or 2 minutes or 5 minutes, whatever. So, here out of A moles per liter of the reactant, X moles per liter of the product has been formed. Now, after 10 seconds, if X amount of the X moles per liter of the products have been formed, means remaining concentration, that is at final, that is at 10 seconds, at the final concentration, it is A minus X moles per liter is the remaining concentration of reactant A. So, based on this illustration, we can directly take the first order reaction. That is, for the first order reaction, if you take the mathematical expression, what is the mathematical expression we can use for calculating the first order reaction? You know pretty well that always whenever we speak about the order of reaction, it is actually a constant called K. K is the rate constant. K is the rate constant which determines the order of reaction. So, take this K, K is equal to, that is 2.303 by T of log A by A minus X is the expression which we can use for calculating the first order reaction. This is the mathematical expression we try to use for calculating the first order reaction. So, the same first order reaction we can also remodify it to, that is time is equal to 2.303 divided by, that is K rate constant, into, that is log of A by A minus X. Then the same expression we can also write it as time is equal to, that is 2.303 into log is equal to ln. So, therefore, I am going to take this as ln of ln 2.303 into log is ln by K into A by A minus X we can take. So, you can just take this expression, same expression, you can keep this expression standby, and this is the standard equation we always try to use while calculating the first order reaction. So, from the first order reaction we can also calculate the half life period of the given reaction. If you are going for half life period, that is half life is nothing but half life, if you take half life is T half, it is T half. So, that means if time is T half, then the amount of product formed is X is equal to A by 2, then we can directly substitute both these conditions of time is equal to T half and the amount of concentration of products formed X is equal to A by 2. If you are going to substitute, then we can directly get the expression, that is T half is equal to, that is 0.693 divided by K. Directly I am going to give you the expression. So, in this expression 0.693 by K, if you expand this, if you are expanding this expression, that is nothing but, that is 0.693 is nothing but 2.303 into log 2 divided by K is the expanded form of 0.693, but 2.303 of log is nothing but equal to, that is 1 ln. So, therefore, this expression, for the further expression you can take this expression as the T half can be also written as T half is equal to 2.303 into log is nothing but ln of 2 by K is one more expression where we can use for half life of the first order reaction. So, we got the expression for the first order reaction as K is equal to 2.303 by T into log of A by A minus X, or you can take T is equal to ln of K, ln divided by K into A by A minus X is one expression, and half life is equal to 0.693, T half is equal to 0.693 by K, which can be written as T half is equal to ln of 2 divided by K. So, these are the two important expressions where we have to use when we are calculating the first order reaction. Apart from this, in the first order reaction we also have pressure change method. So, now after learning the first order reaction with respect to the reactants with respect to moles per liter, that means moles per liter means mostly the reactants are in the liquid state. Now, if you are going for the gaseous state, if the reacting molecules are in the gaseous phase, then for the same first order reaction we can also use pressure change methods. So, my dear students, now let us go to the next part of the concept in chemical kinetics, that is collision theory. It is a very important topic. In collision theory, what we need to understand here is, if you take a container, you can take the number of molecules. These are all, imagine that these are all molecules. When these molecules are trying to collide with each other, no doubt all the molecules they try to collide, they undergo collision. When they undergo collision, due to collisions, every molecule it undergoes certain change in the kinetic energy. You find that molecules acquire kinetic energy, and apart from the molecules acquiring kinetic energy, when molecules are undergoing collisions, these collisions must be effective collisions. That means, whenever the molecules are trying to collide against each other, these collisions, the collisions of the molecule should be effective. So, that means effective collisions, sometimes we can also use the word fruitful collisions. Effective collisions must involve fruitful collisions. If all the molecules, now suppose if you are taking some 1000 molecules in a given container, all the molecules will not participate in the fruitful collisions, because only few molecules will try to acquire some minimum amount of energy, that is kinetic energy. Once they acquire kinetic energy, they start involving in fruitful collisions. Once the fruitful collisions begin in the given molecules, these molecules they have to orient themselves. Orientation of molecules. Orientation of molecules. Orientation of molecules is connected with P. This P we call it as orientation factor. This P we call it as orientation factor. That means, what exactly I mean to say is that the minimum amount of energy which is required by the molecules to participate in collisions, the minimum energy required for any molecule, some minimum energy which is required for the molecule to participate in collision is nothing but threshold energy. Threshold energy, once the molecule acquires threshold energy, then definitely these molecules will participate in fruitful collisions, and apart from that, once the molecules are able to acquire some minimum excess amount of energy in the form of kinetic energy, then that will lead to activation energy. That means, every molecule to get converted into product, it also needs some energy called activation energy. Activation energy is given by EA, and threshold energy is given by ET, E of T, E base T. Already some amount of energy is there within the molecule. Every molecule virtually it has certain energy stored in it. That energy stored, okay, every molecule by virtually it is having certain energy. That energy we call it as, that is En. This En is called normal energy of reacting, normal energy of reacting molecules under collision. That means, what we have to understand here is, what exactly we need to understand here is, there is a relationship between relation between the threshold, this is the relation between activation energy which is given by EA, that is threshold energy ET, and normal energy of the reacting molecules En. What is the relationship? What is the empirical relationship we want to give for these three components? That is, activation energy of the molecules which are trying to gain excess energy to participate in fruitful collisions is equal to threshold energy minus normal energy of the reacting molecules. Threshold energy of the threshold energy and the normal energy. The difference of threshold energy and the normal energy difference, we are going to get the activation energy. So the relationship between activation energy, threshold energy and normal energy of the reacting molecules is given by activation energy is equal to difference of threshold energy and normal energy of the reacting molecule. So if that is the case, this is the relationship we got, and diagrammatically if you want to prove that there is a relationship existing between activation energy, threshold energy and normal energy, suppose if you are going to take a graph like this, y axis and x axis. In x axis we are taking progress of reaction POR, and in y axis we are taking potential energy of the reacting molecules, Now all the molecules which are participating in the fruitful collisions, they begin with certain minimum energy. Okay, that means from the bottom of the curve, if you take, this is the curve you are going to get. This is the curve which we are going to get here. So these are all reactants. R stands for reactants and P stands for products. P for products, R for reactants, POR progress of the reaction, and on y coordinate we are taking potential energy. So if that is the case, then what we need to understand here is, like every molecule will gain certain minimum amount of energy called threshold energy once the molecules acquire threshold energy. So this is the dotted line, this is threshold energy, and if you take the energy of the reactant, if you take a dotted line here, this is energy of the reactant, normal energy of the reactant. I can also take one more dotted line towards the product. So this is the product, this is energy of the product. So if you want to calculate the activation energy of the reactant molecules, so this is the activation energy. The difference of threshold energy and the energy of the reactants is activation energy, that is EA of R, and the difference of the threshold energy and the energy of the products is given by activation energy of the products. So here energy of the reactants and energy of the products difference is going to become this difference, energy of the reactants and energy of the products difference is going to become delta H, that is enthalpy change. We call this as enthalpy change. So enthalpy change is actually equal to the energy difference between, that is energy of the reactants and energy of the products. And if you want to correlate between the enthalpy change and the activation energy of the reactants and activation energy of the products, then we have a generalized equation. Relation between enthalpy change and the activation energy of the reactants and products is given by a change in the enthalpy of a reaction is equal to, that is activation energy forward minus activation energy of the backward. Activation energy forward minus activation energy of the backward. Forward or backward depends upon what kind of reaction we are trying to handle, whether we are trying to handle, that is called energy level diagrams. If you want to utilize this formula, we need to study about the energy level diagrams. Energy level diagrams. We need to study about the energy level diagrams. So in the energy level diagrams, we have two types of energy level diagrams for a given reaction. One is exothermic reaction coordinate energy level diagram and the endothermic reaction coordinate energy level diagram. So we will study how the exothermic reaction coordinate energy level diagram is working out with respect to activation energy and the threshold energy and the enthalpy change, and also we are going to study how the endothermic reaction coordinate will work out with the activation energy, enthalpy change and the reactants to molecules, how they are trying to change in the given reaction. We are going to study in the coming topic. So let us go to an important topic, that is energy level diagrams. Energy level diagrams, and this energy level diagrams also forces us to understand that rate of reaction, that is, I am going to add one more point here, effect of temperature. I will put it like this: effect of temperature on reaction rates. That means temperature has to definitely depend upon the reaction rate. If that is the case, what exactly we need to understand here is, that is, when we are using the word temperature, that means we need to generalize one important point. What we need to generalize is, for every 10 degrees centigrade, increase in temperature, for every 10 degrees centigrade increase in temperature, you find that the rate of reaction or reaction rate is doubled or sometimes tripled or tripled. Suppose illustratively, suppose if I am taking, and you know very well that reaction rate means is nothing but small r is nothing but it is expressed in dC by dt. So its units, moles per liters per second are the units. So that is moles per liter into 1 by second. So moles per liters per second are the units for rate of reaction, that already we know. So if that is the case, now suppose for example illustratively, let us think that a reaction is starting with a temperature of 25 degrees centigrade. If the reaction is starting with 25 degrees centigrade and initial temperature for a reaction is 25 degrees centigrade, and that reaction is ending at a temperature of 55 degrees centigrade, then how does the rate of reaction changes from 25 degrees centigrade to 55 degrees centigrade? So let us understand that at 25 degrees centigrade, if the temperature is 25 degrees centigrade, let the rate of reaction be R. For every 10 degrees centigrade rise, we are already saying that the rate of reaction is going to get doubled. So suppose if I am adding 10 degrees centigrade for this 25 degrees centigrade temperature, this is going to become 35 degrees, then rate of reaction is going to become 2R. Again you add another 10 degrees centigrade, it is going to become 45 degrees centigrade, the rate of reaction is going to become 4R. Again you add another 10 degrees centigrade, 55 degrees centigrade, you find that rate of reaction is going to become 8R. That means almost by the time the temperature is changing from 25 degrees centigrade to 55 degrees centigrade, you are finding that the rate of reaction is almost 8 times than the previous one, because the temperature has increased at the rate of 10 degrees from 25 to 55, means the rate of reaction also it has become 8 times. So this simple logic we have to apply when the temperature is affecting the rate of reaction. However, what we need to understand here is, in the effect of temperature, if you are going to as already we have discussed about the collision theory, in collision theory, let me highlight all the important terms which are useful for us. In the collision theory, Z stands for, that is, fraction of molecules undergoing collisions. That is particularly binary molecules. This Z is applicable only for binary molecules, binary system or binary molecules. That means 2 molecules involvement. Z is the fraction of molecules under collisions. This is one point which you have to remember. Then F is nothing but fraction of molecules. Fraction, that means out of 1,000 molecules, say 100 molecules only are involved in the fruitful collision, means then that value in the form of F, that's nothing but fraction of molecules involved in collisions. This is for binary system. This is for exact fraction of molecules involved in collisions. Also, sometimes we can call this fraction of molecules as pre-exponential factor. We can also call this as pre-exponential factor during the collisions. Then here we can take one more factor which we need to introduce here is orientation factor. So taking these three components into consideration in the mathematical equation, so we can just put it like this. That is, I can say, taking these 3 cases, rate of reaction, if rate of reaction is directly proportional to pre-exponential factor, that is f, then you remove the proportionality, you are going to get z into f. Z is nothing but the number of fraction of molecules undergoing collisions in the binary system. Z is the fraction of molecules undergoing collisions in binary system. F is the pre-exponential factor, and because every fruitful collision again involves the orientation factor. Orientation factor plays a very important role. So therefore, multiply Z and F with the even P also. That is P into Z into F. So because F is pre-exponential factor, F is the pre-exponential factor, then in the place of F, I am going to substitute this rate of reaction. If the rate of reaction is equal to P into Z into F, orientation factor multiplied with the number of molecules undergoing binary collisions is Z. F is the pre-exponential factor. So therefore, this expression I can expand it in this format, saying that R is equal to P into, that is P into Z into, in the place of F, I will take exponential form of minus EA by RT. Exponential form of minus EA by RT. So this is the complete equation which we need to remember. The rate of reaction is equal to orientation factor multiplied with the number of molecules, fraction of molecules undergoing binary collisions in the binary system, and pre-exponential factor F is given by exponential form of minus EA by RT. So this is the expression we need to remember. And one more thing, because anyhow the rate of reaction is going to depend upon the rate of reaction depending on the rate. When the rate of reaction is depending on the rate is nothing but K is nothing but rate constant. So this expression again I will remodify it to, that is, if R is equal to K, so K is equal to P into Z into exponential form of minus EA by RT. This is the final formula which we need to remember. Rate constant is equal to orientation factor into Z into pre-exponential factor, that is exponential form of minus EA by R into T, is the formula which we have to keep it in mind when the molecules are undergoing fruitful collisions, where in which they depend on the temperature. So this is one point which we have to keep it in mind. So from this we can just formulate different relationships, and we can try to understand how the collisions are taking place and how the energy changes are taking place, and from here we can go to, that is, reaction coordinates, that is energy level diagrams. Now after this we will study about the energy level diagrams through the graphs. Yes, my dear students, so now let us go to energy levels, energy level diagrams and reaction coordinates. Reaction coordinates. Reaction coordinates. So here first one I go like this. So first one, this is exothermic, I will put it like this. Exothermic reaction coordinate, one is exothermic reaction coordinate, and the other one is, second one is endothermic reaction coordinate. So what we need to understand here is, let us have some detailed graphical method for this. So I am taking the graph like this on y coordinate. So because in the exothermic reaction, energy of the reactants are greater than the energy of the products. So I will plot potential energy on y coordinate, and on x axis I am going to take progress of reaction in x coordinate, and obviously you can take, because energy of the reactants are greater than the energy of the products. So I will take it like this. The graph looks like this. You can start off like this, you can take it like this. So this is nothing but, these are the reactants. I will take it as A plus B. Imagine that these are the reactants A plus B, and these are the products C plus D. So here if I take, suppose if I am expressing this potential energy in terms of kilojoules per mole, then I can take 10, not to scale, this is only for understanding purpose, 10, 20, 30, 40, 50, 60, something like this. So what is happening here is, like, I am going to take a dotted line for the reactance A plus B, somewhere like this. This is ER, energy of the reactant, and I am going to take a dotted line from the 20 kilojoules. This is energy of the products, and this is obviously this is threshold energy. This is threshold energy. So if you want to calculate the activation energy for the reactants here according to this graph, you can just take, that is, activation energy of the reactants is given by EA of R. From the graph you can easily understand what is happening. Then similarly, if you want to calculate the activation energy of the products also, you can calculate it. Yes, you can take, this is the activation energy of the products. Yes, now from the diagram it is very clear. Now similarly, difference of the energy of the reactants and energy of the products will give us the enthalpy change. But from the graph it is very clear that, if you take the activation energy of the products 60 and 20, roughly if I take 20, if I am going to take 20 here, 20 if you are going to take, if you are finding that activation energy of the products are more than that of the activation energy of the reactant. That's because if the energy of the reactants are more, then the activation energy of that reactant should be less, because in the diagram it is very clear, reactants have more energy. So I am going to just generalize this diagram. What we need to understand here is, if you are going to take, so case 1, from this graph you can understand that energy of the reactant is greater than energy of the product. From the graph you can easily understand that energy of the reactants are greater than the energy of the products. This is first case in the exothermic reaction coordinate. So second case is, if the energy of the reactant is less, then the reactant molecules must have less activation energy. If it is having less activation energy, means obviously from the graph you are able to find that. You are finding that the activation energy of the reactants are less than the activation energy of the products. How much amount of the energy is there for the activation energy of the reactants means, you can just check here, this is 60 minus 40, it is only 20 kilojoules per mole. How much amount of activation energy is there for products means 60 minus 20, which is equal to 40. So obviously from the graph also you can decide that activation energy of the reactants is less than activation energy of the products. Because the activation energy of the products are greater than the activation energy of the reactants, then we can generalize one more expression saying that there's nothing but enthalpy change. Now you can take, because activation energy of the products is more, so enthalpy change is equal to, of course enthalpy change is always equal to the difference of activation energy of the products and the reactants, but because here anyhow activation energy of the products is more, so therefore activation energy of the products minus activation energy of the reactants. This is what you need to keep it in your mind. We have to understand that energy of the reactants is more in the this is exothermic reaction coordinate, mind you. Don't forget that this is exothermic reaction coordinate. By the time the reaction is completed, the energy of the reactants, once all the reactants are able to acquire the minimum energy called threshold energy, all the energy whatever is there in the reactants, that energy has to be dissipated. It has to lose the energy such that from 40 kilojoules now the energy of the products have become only 20 kilojoules. That means the energy which is present in the molecules has been sent out from the system into the atmosphere. So therefore when the energy is less, automatically all the reactant molecules are getting converted to products. By the time the products are formed, we are finding that the energy of the products have been already reduced to only 20 kilojoules, where initially the reactant molecules were having 40 kilojoules. So therefore you are finding that this is how the reaction coordinate will behave in terms of exothermic reaction. If you are able to understand what exactly is happening in the exothermic reaction coordinate, you can easily understand what is happening in the case of endothermic reaction coordinate. Just draw the graph exactly reverse to what you have learned here in the case of exothermic reaction coordinate. So my dear students, let us switch on to the next part of the reaction coordinate, that is endothermic reaction coordinate. Go to the endothermic reaction coordinate, take the y-axis, and take the x-axis. Again in the x-axis you take progress of the reaction. In the x-axis we can take potential energy in y-axis expressed in kilojoules per mole. The only thing is that in the endothermic reaction, because all the molecules they try to gain energy, before itself they try to gain the energy, and the molecules will not allow its energy to leave the system. That's why what we have to understand here is all the product molecules must have more energy than the reactant molecule. So reverse this graph slightly, tilt the graph. So this is how the graph looks. The graph goes like this. This is the graph, slightly opposite to the previous graph. Higher elevation to lower elevation. This is lower elevation to higher elevation. So therefore, here you can take again, this is A plus B, same format, A plus B are the reactants and C plus D are the products. C plus D are the products. And chalo, now let us let us try to graphically represent the energy of the reactants. Imagine that this is 20 kilojoules, then this is 40 kilojoules, then 60, then 70, and of course 80, something like that, 80 kilojoules. Energy of the reactants, then this is energy of the products. This is energy of the products, okay, and this is threshold energy. So once you know the threshold energy and the energy of the products and threshold energy and the energy of the reactants, you can easily identify, you can calculate what is happening to the activation energy. So here activation energy of the products, this is the activation energy of the products, and here this is the activation energy. Okay, I am just taking over here. This is activation energy of the reactants. You are finding that activation energy of the because energy of the products is more, the activation energy of the products have become less. Energy is more for the products, so its activation energy is less. Energy of the reactants is less, so its activation energy is more. From the graph, it is very clear for you to understand how the activation energy and the energy changes are taking place between the reactant molecules and the product molecules. So that means from this graph, again, just exactly the reverse conditions, whatever we have adopted for the exothermic reaction, we have to adopt the opposite conditions for the endothermic reaction. So in the case of endothermic reaction coordinate, this is endothermic, mind you. If it is endothermic, yes, the first condition is you are finding that the energy of the products, this is products and these are the reactants. These are the reactants. So here you have to say that energy of the reactants is less than the energy of the products. Henceforth, you have to find that because the energy of the reactants is less than the energy of the products, you are finding that the activation energy of the reactants is more, because lesser energy means more activation energy. So activation energy of the reactants is more, activation energy of the reactants is more than the activation energy of the products. So therefore, if you want to calculate the enthalpy change, where is enthalpy change? This is the enthalpy change. The difference of the energy of the reactants and energy of the products difference is enthalpy change. So take the enthalpy change, that is enthalpy change is equal to, because activation energy of the reactants is greater than the products. So therefore, I can say that this is activation energy of the reactants minus activation energy of the products. Is the formula which we can use for calculating the enthalpy change for the endothermic reaction coordinate. So this is how we can understand the reaction coordinates for exothermic reaction coordinate as well as endothermic reaction coordinate. Now after this reaction coordinates, now we will slowly enter into the, again we will go back to the effect of temperature that is affecting the rate of reaction, and now we are going to learn about the Arrhenius equation of interpreting the rate of reaction with respect to temperature and the activation energy changes. Okay, my dear students, let us learn something about Arrhenius equation. Arrhenius equation for temperature dependence. Temperature dependence on rate of reaction, on rate reaction, rate equation, we can say whatever. Arrhenius equation for temperature dependence. Arrhenius equation for temperature dependence on the rate of reaction. So temperature dependence, I can say dependence, temperature dependence on rate of reaction or rate equation. So directly I am giving you the formula, K is equal to A into exponential form of minus EA by RT. Let us slightly modify this expression. This is the Arrhenius equation. So here K is the rate constant. Let me just put it K is the, let me highlight all the terms. K is the rate constant of rate equation. Then A is the Arrhenius constant. Arrhenius. A is the Arrhenius constant, and EA is the activation energy. Is the activation energy of the reacting molecules, and T is the temperature. T stands for temperature. So what we need to understand here is, suppose if I am removing this exponential form, in the RHS side, if I remove the exponential form, the same expression I can write it as ln of k is equal to ln of A of minus EA by R into T, R into 1 by T. Or the same expression I can write this as, or the same expression ln of k is equal to minus EA by R into 1 by T plus ln of A. Convert this into equation of straight line. Convert this expression into equation of straight line. This is y is equal to mx plus c is the equation of straight line. So y represents the y coordinate, where we can take ln of k, and x represents reciprocal of temperature 1 by T. M is the slope, so minus EA by R is the slope, and this A is nothing but Arrhenius constant, that is ln of A. So suppose if you plot a graph, let us plot the graph also. If I am plotting the graph, then on y coordinate I am taking ln of k is the y coordinate, then x coordinate I can take reciprocal of temperature. Then because the slope is negative here, so we get a straight line with the negative slope. So m is equal to, that is m is equal to minus EA by R, and because intercept is there, the intercept is extrapolated on the y-axis somewhere here, and here you find that this is nothing but intercept, that is C is equal to ln of A. This is what we are going to plot the graph for the Arrhenius equation in terms of the ln form. But the same expression, suppose I am taking this expression, let this be equation 1 and let this be equation 2. From equation 2, let us take from equation 2. If I take, that is ln of k is equal to ln of A minus EA by R into 1 by T. 1 ln is log base E, and log base E of ln is equal to 2.303 of log base 10. So 1 ln I can just take it as 2.303 of log. I can take 2.303 of log k is equal to 2.303 of log A minus EA by R into 1 by T. Divide LHS and RHS with 2.303. The same expression we can write it as log k is equal to log A minus EA by 2.303 of R into 1 by T. 2.303 of 1 by T. So that means let this be equation, or I will write the same expression as log k is equal to, that is minus EA by 2.303 of R into 1 by T plus log of A. Again this we can convert this into equation of straight line. Convert this into equation of straight line, that is y is equal to mx plus c. Plot the graph, same graph almost we are trying to take, but in the log form we are trying to take. So in the x-axis we are taking log k, and in the y-axis in the y-axis we are taking log k, and in the x-axis we are taking reciprocal of temperature, and we got a slope, negative slope we got. So if it is negative slope, straight line with the negative slope, m is equal to minus EA by 2.303 of R, okay, and we have also intercept. So this is the intercept, that is intercept C is equal to, that is log of A. This is log of A. This is the graph where we can plot. But in this expression what we need to understand here is, there is a chance for the, because rate constant, rate of reaction depends on temperature. If rate of reaction is depending on the temperature, rate constant also depends on temperature, because R smaller, rate of reaction depends on rate constant. If rate constant changes, rate of reaction also changes, and rate constant definitely depends on temperature, because we already knew that the rate of reaction depends upon the temperature dependence of rate of reaction. So therefore, rate constant definitely depends on the temperature. So therefore, if there are two rate constants, for two different rate constants for K1 and K2, if there are two different rate constants, then definitely temperatures are, for rate K1 and K2 are the two different rate constants, then temperatures also will change, that is T1 and T2. Then this expression can be slightly modified as log K2 by K1 is equal to minus of EA by 2.303 of R, EA by 2.303 of R into 1 by T1 minus 1 by T2 is the expression which we can take for comparing the two different rate constants K2 and K1 with respect to T1 and T2, keeping the activation energy of the reaction constant. So this is the Arrhenius equation for the temperature dependence for a given rate of reaction with respect to two different rate constants. Log K2 by K1 is equal to EA by 2.303 of R. R is the universal gas constant. R value depends upon what values you are taking, what units you are taking for activation energy. So universal gas constant is R. 1 by T1 minus 1 by T2 are the temperature differences for the two rate constant, that is K2 and K1. So this is the empirical relationship for the Arrhenius equation for temperature changes as well as rate constant changes. So my dear students, let me finish off one last part in this temperature dependence on the rate of reaction. That is, in the temperature dependence of the rate of reaction, earlier already I gave you one expression, K is equal to, that is Z into P into exponential form of minus EA by R into T. This expression already I gave you. So here P stands for orientation factor. Orientation factor. That means what exactly we need to understand here is when the molecules are undergoing fruitful collisions, these molecules they need to undergo proper orientations. When they undergo orientation, then only they can develop the activated complex. Once they develop the activated complex, old bonds will break and new bonds can be formed. For example, if you take example 1, if I am taking, suppose if you are dealing with H2 gas plus I2 gas gives rise to 2HI gas. I mean, these two are reactants participating in fruitful collisions, and these two molecules of HI which is formed, hydrogen iodide which is formed, is nothing but product. These are the product. 2 moles of HI are the products formed. Okay, fine. But what we need to understand here is, you know very well that H2 molecule contains one single covalent bond, and I2 molecule also contains one single covalent bond. Of course, iodine is a sublime solid. It has sublimation property, so it exists in the vapor phase. Okay, we can regard it as a gaseous phase. So these molecules, when they are trying to colloid, undergo collision, or else we can say when they undergo collisions, they give an intermediate complex called activated complex. What do you mean by this intermediate complex or activated complex? That is, if I take two molecules of HI like this is called, this complex we call it as intermediate complex, also called as activated complex. That is activated intermediate complex called activated complex. When activated complex is formed, what we need to understand here is, it is very interesting to find that these are the old bonds, and you can see some dotted lines here. So the dotted line represents that both the H2 molecule and I2 molecule, they are trying to orient themselves in a definite pattern. When they try to orient themselves in definite pattern, they become automatically activated complex. That means this is called the orientation effect of the two molecules. So that means what is happening here? The next final product here, that means old bonds have to break. This bond will break. The old bond is going to break and the new bonds are going to form. When the new bonds are formed, it is going to result in the formation of same molecules of HI only we are going to get, but new bonds in new direction we can get. So the direction of the bonds have changed from the old bonds have been broken and the new bonds have been formed, but the expected product is same. But the expected product is same with proper orientation. It is because of effective orientation of H2 and I2, okay, it is giving HI molecules. Even in the case of substitution nucleophilic reaction also, in the case of SN reactions, if you take SN1 reaction in particular, you find that tertiary alkyl halide, if you are going to take tertiary alkyl halide, for example, if this is the tertiary alkyl halide, that is R, R dash and R double dash, 3 different alkyl groups I am taking, and here we have a halide. The incoming nucleophile, if it is going to attack the stereogenic carbon from the front side, this is called front side attack, then you find that there is no question of any formation of products. You don't find that if the incoming nucleophile OH minus is the nucleophile, if it is coming in attacking the stereogenic carbon from the front side, this carbon halide bond will not break and there is no question of formation of any bonds. I mean, you mean to say here a kind of repulsion takes place, even if the product formation takes place also, it is very difficult. Actually, you find that some kind of repulsion occurs here. This is minus, this is plus, and here also this is OH minus. You find that certain amount of repulsion takes place because both the outgoing halide ion also, it is a sort of nucleophile only, it is a better leaving group. So therefore, the halide ion and the incoming nucleophile OH minus, both of them they try to undergo certain kind of unwanted repulsions. So therefore, ultimately no products are formed. So when no products are formed, then how could we see that it can produce orientation effect? That means this incoming nucleophile, it can attack the stereogenic carbon from the back side as well as front side. So that means the orientation effect, in the orientation effect, you can take the orientation effect like this, that is, take the same alkyl halide, that is R, R dash and R double dash. If you take, it becomes a carbocation. Now if the incoming nucleophile comes, it can attack from the front and back end. Of course, here tertiary carbocation is formed because polar protic solvent favors the SN1 reaction, releasing the weaker nucleophile, that is better nucleophile, leaves the stereogenic carbon, that is carbocation. Once the carbocation is formed, now the nucleophile can attack the carbocation, stable carbocation from both the directions, from the front side and back side. Yes, definitely you find that proper orientation is taking place. Once the orientation is taking place, you find that here the tertiary alcohol, you are going to get R, R dash of R double dash and plus X minus. So I can say that this leads to proper orientation effect. Leading to formation of products. Effective orientation or proper orientation leading to the formation of products. Leading to formation of products. Leading to the formation of products. Likewise, one last factor also I will finish off, the last factor, that is fifth factor which is affecting the rate of reaction, that is effect of catalyst. Let me finish off this. If I am going for effect of catalyst, you know pretty well that catalyst is nothing but a substance which is added into a reaction where it can only alter the rate of reaction. That means depending upon the type of reaction which we are trying to handle, a catalyst can sometimes increase the rate of reaction or sometimes it can decrease the rate of reaction. So catalyst can be a positive catalyst or negative catalyst. But however, here in this case of kinetics, we have to understand that catalyst can favor the reaction. Catalyst can change the path of the reaction in the reaction coordinate by lowering the activation energy and bringing the completion of the reaction at a faster rate. It decreases the activation energy and completes the reaction at a faster rate. So again, I am going to take the same graph as how we have studied in the reaction coordinates, taking potential energy on the y coordinate and progress of reaction on the x coordinate. Imagine that you are getting a reaction coordinate curve without catalyst, without addition of catalyst. Imagine that this curve is having an activation energy equal to EA, but after this is without addition of catalyst, without catalyst, say the rate of reaction is R1. Of course, this is A plus B and this is C plus D. Now, once you add the catalyst, you find that there is a change in the path of the reaction coordinate. The path is, it describes a new path by lowering the activation energy. By lowering the activation energy, this is a new path which is described. This is the new path which is described after the addition of catalyst. So, this is EA dash, this is after addition of catalyst. This is R2. So, from the graph, after the addition of catalyst, because the activation energy is lowered, if you compare, that means if EA dash for the addition of catalyst, if EA dash is the lower kinetic energy, lower activation energy, E dash is less than EA, then automatically R2 is greater than R1. Lesser is the activation energy, more is the rate of reaction, is what you need to understand the effect of catalyst on the rate of reaction. So, when catalyst is added, the path changes in the reaction coordinate, lowers the activation energy, reaction goes for faster completion, and the new rate is going to be the faster rate, where it allows the reactants to convert into products at a faster rate. So, my dear students, in chemical kinetics, if you go for second order reaction, in second order reaction there are two cases. One is if both the reactants are same, that is A plus A gives rise to products, P for products here. If two reactants are same, the same thing you can write it as 2A, means you can just write this as A plus A gives rise to products. If the two reactants are same, then the second order reaction, under such case, if the two reactants are same giving rise to products, then the rate constant for the second order reaction is given by 1 by A into T of X divided by A minus X. What do you mean by this? This means that if you are taking two reactants, A of A gives rise to products, it means that initially, in the initial stage, you find that A moles of, let the initial amount of concentration for both the reactants of A and A, which are two same reactants, this is A moles per liter and A moles per liter. No products have been formed when the time is scaled equal to, that is 0 seconds. After a lapse of T is equal to T dash, where T dash is greater than T. You find that out of A moles per liter of the initial concentration of A, then B moles per liter of the products have been formed, and how much amount of the reactants, or you can, because in the expression we have already used X, no, so I will just change this B to X. I will take X moles per liter of the products have been formed. How much amount of the reactants are still present after a lapse of T is equal to T dash, where T dash is greater than T, means this is final. In the final stages, we can take this as A minus X of A minus X. So, from this illustration of the second order reaction, where both the reactants are same, we are taking the expression rate constant is equal to 1 by A into T, where small a is the initial concentration of the two same reactants A, and X is the amount of product formed, and A minus X is the concentration in moles per liter for the products formed, and A minus X is the remaining concentration for both the reactants of two molecules, that is A of A. So, basing on that illustration, we are taking K is equal to, rate constant is equal to 1 by initial concentration of the reactants into time into, that is amount of concentration of products formed, divided by remaining concentration at the lapse of time T dash is greater than T. This is for two same reactants. But suppose if for the same second order reaction, if two reactants are different giving rise to products, then for the same case we can take again one more illustration. A plus B gives rise to products. A plus B gives rise to products. Initial concentration, if you take initial concentration small a plus small b, initial concentration is, that is, say A moles per liter of the initial concentration, initial reactant A is For the initial reactant A, its concentration is A moles per liter. Initial reactant B, its concentration is B moles per liter. This is B moles per liter, 0 when the time is scaled as 0 seconds. Initial concentration of the reactant is A moles per liter, and for the other reactant it is B moles per liter concentration. Then when the time is 0 seconds, no products have been formed, so it is 0 moles per liter. But when the time is lapsed where T is equal to T dash, that is T dash is greater than T, then here we can find that if X amount of products have been formed, then obviously this is going to be like A minus X, and this is going to be B minus X after lapse of time. So this is going to become final. So based on this illustration, we got a new expression for the second order kinetics, that is rate constant K is equal to 2.303 divided by T into A minus B into log of B of A minus X divided by A of B minus X, where here B is the A and B are the initial concentrations of two different reactants A and B, then X is the amount of product which has been formed, and the remaining amount of concentration after the final reaction is going to be A minus X is the remaining concentration for the reactant A, and B minus X is the remaining concentration for the reactant B. So taking this A minus X and B minus X as the remaining concentrations and in the final stages for the second order reaction of two different reactants A and B, we got this expression as K is equal to 2.303 divided by T into A minus B into log of B of A minus X and A of B minus X in the denominator. So based on this, this is the second order reaction. So in the second order reaction, for the second order reaction, generally for second order reactions you can take plenty of examples, like I can take SO2 for examples of second order reaction. If you take sulfur dioxide plus chlorine gives rise to SO2 Cl2, that is sulfuryl chloride. Sulfur dioxide reacts with chlorine to give sulfuryl chloride. So if you want to write the rate equation, rate of reaction is directly proportional to concentration of SO2 to the power of 1 into concentration of chlorine to the power of 1, where if you remove the proportionality, you are going to get rate of reaction is equal to rate constant into concentration of sulfur dioxide to the power of 1 into concentration of chlorine to the power of 1. This is one more step. So it is very clear that from the rate equation, formation of sulfuryl chloride from the two reactants sulfur dioxide and chlorine will obey the second order reaction, because the sum of the powers of the molar coefficients is to the power of 1 and to the power of 1. And like that you can take even one more example, second example for second order reaction. Example 2, that is PCl3 plus Cl2 gives rise to PCl5, simple reaction, that is formation of PCl5. So this is going to be rate of reaction is equal to rate constant into concentration of PCl3 to the power of 1 into concentration of chlorine to the power of 1. So this is a second order reaction. So that means these are two different cases which we need to understand in the case of second order reaction, that is for two same reactants and also two different reactants, and this is about second order reaction.